Assalamualaikum and good morning. For this video, we'll be doing chapter summary for chapter 1. Physics chapter 1, second semester is electrostatics. So for chapter 1, we have few subtopics that we are covering. So first we have the Coulomb's law. Coulomb's law is about electrostatic force. First, this is the basic equation of the Coulomb's law. So you have F equal to kq1 q2 over r squared, and r is the distance between two charges. So what you have to know about the Coulomb's law is, because force is a vector quantity, so before you do your calculation, you have to sketch the direction. So first thing first, you have to know the interaction of forces when you have same charges, positive positive, negative negative, or opposite charges. So basically same charges will repel, and you have opposite charges, it will attract. So that's the direction of forces that you can sketch. And we have kq1 q2 over r squared. This is the basic equation for Coulomb's law that you are going to apply for your calculation. And you have, for the second quantity for this chapter, is electric field. And for this quantity, you have to know that positive charges will have outward direction of electric field from the charge. Negative charges will be giving you inward direction of electric field in any angle. So this is the basic equation for electric field, is the force experienced by each unit charge. Okay, so meaning that if you have a region of electric field, it is proved that that region consists of electric field because of the force experienced by the charge. So we've already have the equation of force from the Coulomb's law just now. Okay, so we can substitute in this equation, and finally you'll have your E is equal to kq over r squared. E is also vector quantity, that's why you do the sketching of the direction first before you do the calculation. Another equation for electric field is E is equal to delta V over D. So this is special because this is for point charge. The first equation is for point charge, and the second equation is for electric field between two parallel plates. We call electric field, the second electric field here, as a uniform electric field. Okay, in the last subtopic for this chapter, you actually have specific subtopic for uniform electric field. You have few cases, case number 1, case number 2, until case number 4. So for all of these 4 cases, you are actually applying this basic equation. Okay, E is equal to V over D. Then you have electric potential. So the basic equation for electric potential is work done per unit charge, or electric potential energy per unit charge. Okay, so you have the equation kq over r for electric potential. So sometimes in your case you have a few charges in certain area, so to get the electric potential experienced at certain point, so you need to add up all the potential contributed by each charge. So one charge will contribute one potential. So in this case, for this example, you are actually having 3 charges. So, okay, one charge will contribute one potential. And apart from that, you also have delta V. Delta V is the potential difference. So it's V final minus V initial. Okay, then you have electric potential energy. Okay, again it is equal to the work done. So it's kq1 q2 over r, and electric potential can also be expressed as q delta V. Okay, if you have the change in electric potential, so q delta V, and delta V is the potential difference that we've got earlier here, potential difference. And if you have a few charges, okay, question asks you to calculate the electric potential energy for this system. So you are going to add up all the possible energy interacted by 2 charges in the equation, any 2 charges in the system. So for this case, you are actually having charge number 1, number 2, and number 3. So you have 3 terms here, 1, 2, 3, the possible interaction. And then for the last subtopics, you have, like I said just now, uniform electric field, stationary charge. So basically, this is for all the cases here, 4 cases here, it is the case for uniform electric field that is in between two parallel plates. So stationary charge means the charge is stationary in between the two plates. Charge moving perpendicularly to the field. So you have, for example, and let's say you have charge moving perpendicularly. This is the electric field. It is from positive to negative, uniform. You have a few lines here supposed to be drawn. So it will enter perpendicularly. The path taken by this charge is going to be parabolic. It will go to negative charge because it is positive, so it will be attracted to negative charge. So basically, all the charges that is in between the two plates, it is experiencing a force, because it is tend to be attracted to any of these two plates. It's either positive or negative. So this force here will contribute the motion of the charge. So we have F equal to ma. Since we have the force here is contributed by the electric field in between, for example, we have E here. So equation of force here is QE equal to ma. You can use this equation to calculate so many things. For example, you can calculate acceleration, or the question might ask you to calculate the electric field strength. So this equation applies for all these 4 cases. Case number 3 is the one that I've told you just now. So moving parallel to the field means you have charge. For example, it is positive here, so attracted to negative. And last one is for charge in dynamic equilibrium. For this charge, we are considering the weight. So if you expand the equation, it's QE equal to mg. And just for a reminder for you, for F and E, both are vector quantities. So for calculation, we need to ignore the negative sign. And for V and U, it is scalar, and we cannot ignore the negative sign in the calculation. You have to include the negative sign of charge in the calculation. So that's all for chapter 1, electrostatics. Thank you very much.